This
Exchanger
conference will now be recorded.
work stream. Sorry, I just forgot to recording. Um, let me share my the notes for today, um, the agenda for today, and then also the notes for the last time. Um, just give me 1 second. Uh, so for today's agenda, so I'm gonna asking the community about any questions you guys have about the pre-notes I posted it on the group. So to kind of go over quickly, we kind of discussed about a couple options for the real heat exchanger, and also we talk about the environmental conditions that the real heat exchanger is going to be operating it. And altitude, we also talk about the delta T. We wanted to stay 22 Fahrenheit delta T, greater than 22 Fahrenheit delta T, and CFM per watt corresponding to 22 Fahrenheit delta T, which is about 0.145 CFM per watt. We also kind of discussed about how to width. I think there's more things to be considered when we, um, the pitch of the direct rack, or the width of the HADA that we should suggest to the data center. And we also talk about the serviceability wise. We probably want some heat door or something similar mechanism. And heat exchanger size, since based on the YD2, 600 millimeter is a nominal width, and 22 tenths for the height. And the depth is something that we also want to define over the time. The cooling capacity, we talk about 25, 35, and 50 kilowatts. I think there's multiple use cases for different cooling capacity. Um, and we also talk about where the CDU or chill water should be connecting, either top or bottom, which I don't think we haven't discussed detail yet. Hopefully, we can cover that in next meeting. Probably not today. Do you guys have any questions about the, no, the notes from the last meeting?
No, not yet.
Okay, awesome. So I just want to have a quick discussion about some of the options we discussed. Let me open up the the slide that we share. So one of the options was the last time we called that the passive is going to be more like a rack fan or system fan, um, and also the active is going to be more like having a cold plate attached to the heat source, and then using the rear door heat exchanger to cool the water. Um, However, I got a feedback from some community that the the way the definition way we're defining the passive and active is not really aligned with the industry definitions. So I just wanted to have quick discussion how we should be called out that more aligned to the industry. As I know that the passive is we call passive yield over the changer when we that's the definition of when the fans are located in the system. Is that right?
Yeah, that makes sense to us. Sorry, this is Jason from Cool IT. When we are operating with rear doors, we have kind of both passive and actives from a few of our partners, and the passives are always essentially just a coil that the server fans are blowing across, and the data center is pulling air from. Whereas active would actually have fans mounted directly to the rear door. But that's really to us the main definition difference.
Awesome. So I guess question is what is the kind of the good way um, to to call it for this type of concept?
So in this case too, we have a product that works similar to this. It's not technically a rear door, but we are using kind of a liquid to air CDU with heat exchanger, where our product sits in the bottom of the rack. It's rack mounted, it has a pumping system that's driving liquid directly to the cold plates and then back to a radiator that's blowing off to atmosphere. So it would be more akin to an active rear door, but it's not actually a rear door. It's like a 5U appliance that sits kind of at the bottom of the rack. So in this case, we're not calling it a rear door because it's not. But if you were to design one like that, I don't know if it would be a third design or it would just be an active rear door. I think there'd be no major difference.
Yeah, but I guess active rear doors could be quite a confused definition with the actual, active rear door heat exchanger that we kind of described in this context with the rack fans attached to the rear door heat exchanger, right? I don't know, because I'm suggesting maybe we can call it out like a hybrid rear door heat exchanger or a hybrid in-rack.
Hi, Jacob, it's Ronald from Further speaking. If we're talking about cold plate, we're talking about direct chip cooling, and if you combine that with a rear door heat exchanger, you're mixing two solutions, and of course it's possible, but the question is how feasible is that? Why would you do that? Because normally you would choose for one or the other.
So this is Martin Dörch from Rittal. So I think I do have the same opinion. We are here mixing up two different solutions. And as far as I understand, so the direct liquid cooling is a topic of another ACS group. So as I understand, we do have the rear door heat exchanger and the integrated fans inside the IT systems push the air directly over the big coil integrated in the rear door, what we call, passive rear door.
Agreed, the same here. We do the same thing. And of course, again, you can combine the things, but the rear door has nothing to do with the cold plate systems. It's just they need both chilled water. But that's the only thing they have in common.
Yeah, and to clarify, I think for this active rack solution, if this did exist, the rear doors would need a pumping solution integrated. Normally, rear doors have no pumping system, so that would be one major difference.
Agreed.
Yeah.
And also, normally the fluid you will apply to the chip cooler, so the cold plate coolers, would be ultra low pressure because there are small tubes, so it's not connected to the normal chilled water where a rear door is normally connected. You will need an additional heat exchanger then.
Yeah, for direct chip cooling, you need a kind of, let's say, a manifold for liquid distribution, and to that manifold, all the different heat sinks inside the server, for example, is directly connected via quick couplings or something like that.
Correct.
I think the way Jacob has it in the drawing is that yes, I mean the heat exchanger by itself. The heat exchanger by itself would not be directly coupled to the cold plate, right? You'd have to go through some sort of CDU. But the CDU is only responsible for driving the internal loop, right? So there would be no plate heat exchanger that is usually involved when you have facility water. I think this use case is being described for a case where facility water is not available. And how can you use cold plates in such a case? Well, you could use it. You could have an internal closed loop in the chassis, but if there are too many chassis, then it's better to move the radiator to the rack. And I think that is what Jacob is describing.
So, yeah, I mean, I guess one of the kind of the use. I mean, one thing that I was kind of thinking about is we are not. If I look at the overall the cooling problem that most of the key components are sitting in the system that has to be somewhere that heat has to be extracted from the system. And in case that when the data center is not 100% ready for providing the facility water, how can we have some sort of large water heat exchanger type of solution that could cool the hot chip in systems by using the CPU and a cold plate solution. And I think cause I mean, one of the kind of difference that I can think of with the cold plate workstream could be maybe, I mean, I can't really represent what really defining the work of the cold plate workstream at this moment, but you can see that the cold plate workstream might be more defined with the facility waters ready. And while this one, and maybe they don't need a real heat exchanger type of solutions, they might have a more liquid to liquid exchanger. And while here we're using the liquid to air heat exchanger to cool the water for the second internal loop within the. Does that make sense?
I think at the end of the day, you need cold water anyway. First possibility that is that the cold water is provided by a facility chiller, or if there no facility chiller is available, you have to place a separate chiller to provide the cold water. The CDU is good for, how to say, doing a kind of second loop in the data center to avoid to have dirty water from the facility chiller on the data center side, or to avoid to have too cold water on the data center side, because if you use heat exchanger, you always have to be above dew point, because it's really hard to do any kind of condensate management. So from my point of view, you need a CDU to do these different issues.
So just to weigh in on that, you don't necessarily need to use a facility chill or rear door heat exchanger. You could use the return water from existing fry units if it's a hybrid application. You could also have a cooling tower where you're actually leveraging the water from the cooling tower. And naturally, you want to have a secondary brazed plate heat exchanger that's going to isolate the primary building loop from the secondary loop in the white space. It's also really important to pay attention to your water quality on the secondary loop in the white space, because really these systems are quite reliable unless you have corrosion within the secondary loop, which could cause potential for leaks over a longer period of time. But there's certainly multiple methods to reject the heat outside the data center beyond using dedicated cooling plant.
For sure, agree.
Okay, so I guess
I think also, just to comment on the dew point, I mean, 57 or 58 Fahrenheit is kind of an average dew point for most data centers that are properly sealed. So if you're using, let's say you're using 65 degree or 74 degree water from your cooling tower, it's quite achievable without much risk of condensation.
all right. So I mean, kind of going back to the original question that and what would be the kind of the way to call this concept to align with the industry? I was thinking more like a hybrid solution. Would that be a good name for this concept?
I think is a good placeholder for now. It at least describes that it's a unique offering. It's not a typical rear door passive or active. It's some kind of hybrid solution.
Yeah, I mean, we can let's start with the topic for now. Then once we have a better name, please suggest how we should call it, and that's more aligned to the industry. Now, going back um, to the second topics, I'd like to discuss about the definitions. Oh, I'm sorry, the third topic. So discussion about the application of the active and passive real heat exchanger. Um, so I think this is also one of the topic we would like to discuss this evening in the last pre-note. I just wanted to know how communities are thinking about where this real heat exchanger will be applied, and what's going to be the best, what are the benefits of using the real heat exchanger in the data center?
So the big pushback or knock on passive rear doors over time has been concerns about pressure drop across the coil and the potential to actually cause the IT fans to speed up to deal with that additional pressure drop. And there's studies that support that concern, and there's studies that mitigate that concern. But another approach with I guess an active rear door, which maybe addresses that concern to a degree, right, is removing the fans from the IT altogether. So if this is being used, let's say with a direct-to-chip technology, an active rear door might be interesting in allowing a draw-through design where you're using a direct-to-chip liquid cooling technology to deal with the CPU or GPU, and then you're using an active rear door with no IT fans.
Interesting. Is there any benefit for using either active or passive heat exchanger? Is there anyone in the community who are actually using this technology and getting the benefit?
So we installed when I was running Pulcentric or VET, we were the first company to commercialize rear door heat exchangers, and we installed over 1,000 units in the field with, and these were passive units without any issue. The downside is you do have to leave a bypass area to lower the pressure drop, and you have to have a very specific coil design to have a low pressure drop to mitigate the potential for effect on the IT fans. Naturally, the benefit of going with a passive rear door is that you're eliminating the air cooling fan power, so you're getting much higher efficiency than with an active rear door.
Yeah, here, Ronald van Veen, Furtive, I agree. The pressure drop will increase the amount of energy used by the IT fans. That's true, but you lose your fans that you normally have in your air handling units, and the air loop itself is much shorter, so there's less energy needed to move the air from the cooled air back again in the IT equipment. So it's a relative short loop. And as long as you keep it passive, you don't need controls, you don't need electrical connections. So it's also very robust from a reliability point of view, because there are no controls needed for airflow. And the gain is the hot zone is within the rack, so you're able to go higher than in a normal data center where you have to allow a maximum for the hot aisle because people have to be there. And here it's contained within the rack. And once it leaves the coil, it's room temperature again. It's inlet temperature again. So that has to be the benefit. And of course, resilience. If you have a lot of racks, say 100 racks or more in a room, and you lose one backdoor cooler, you only lose 1%.
Yeah, I mean, a kind of ideal way. I mean, a couple things like what the benefit for this concept are one, no containments required, maybe. That could be significant process and cost saving data center. Or we can also minimize any concerns about recirculations happening because the way that it works is the recirculations is actually a better for capturing all the air. And second is maybe
You can eliminate cracks.
yeah, we can eliminate the crack units, or another way to say that is we can have better real estate benefit.
Yeah, I agree with both of your comments. One comment to add though is in a way using a rear door heat exchanger with a liquid cooling approach, there is a downside. The downside being that the biggest effect on the capacity of the coil is going to be the delta T across the server. So by mitigating, let's say 70% of the heat through let's say a direct to chip approach, the delta T is going to be affected negatively from the standpoint of the capacity of the coil. Now, what you can do there though is go to a different coil design, which is a lighter duty design depending upon the total heat load. It depends on compaction and how much IT heat load you're dealing with in general. But there's some fine tuning, obviously, that can be done with the coil selection on the rear door heat exchanger for a much lower pressure drop, based on the fact that about 70% of the heat's being removed through the liquid cooling loop.
Sorry, do you mind elaborating on more compact heat exchanger designs?
When I mentioned compaction, I was talking about, let's say if you eliminate the fans from the IT, and you're removing the air-cooled heatsink and replacing it with a liquid-cooled heatsink, there could be some IT designs, let's say 4U or 2U IT designs, where you can go down to less use space. So in essence, higher density per rack per server.
So wait, hold on. So I think when you say cold plate or liquid type of heating solution, that probably more fitting into a hybrid real heat exchanger, right? Okay. Which is our kind of the next topic.
Yeah, I agree. That's more of a hybrid. Yep.
Okay. What will be the kind of the downside? I mean, one of the downside for this concept is that it can give us, as I think it's kind of aligned to the hybrid, is when especially we're still relying on cooling the hot chips with some sort of heating type of solution. So although we are getting some density of power density of the rack for the cooling, or maybe the cooling benefit of in a rack level, but we don't. I think that the cooling level in server level is going to be quite limited with this approach. Do you all agree with that? So what I mean is that if CPU or maybe GPU become, I don't know, maybe 500 watt, 800 watt, even maybe 1,000 watts, this type of solution is still difficult to cool those chips unless the server has to come up with its own solutions to cooling the 1,000 chip to make this to work.
Agreed, but a rear door heat exchanger is an air-based cooling system. So Of course, you have to dissipate the heat of the components to the air. That's the rear door system. And if you want to do something else, it's a chip cooling solution, and you're away again from the rear door heat exchanger benefits.
Well, I mean, we are dissipating the heat through the coil, right? So that's why kind of going back to the concept of the hybrid, which we can attach into some sort of a coil, so we can kind of cover both system level cooling and then also the rack level cooling, and then still within the air cooling system. Is that?
Yeah, but I think if we look at the hybrid, to be honest, and let's say we catch 80% or something in a direct chip cooling, and only 20% is left for conventional cooling, I would say, okay, that's relative low power. Let's use traditional room cooling systems, square systems, because to be honest, a backdoor system is more expensive. And the gain is that it can do high amounts of energy for a relative good solution with high temperatures and chiller-free solutions. But if it's only 20% you need to do, it's an expensive 20% to cool.
So, Ronald, I think you can look at it both ways. If you're talking about dealing with the remaining 20% of the heat load using perimeter crawl units, the downside is you're still maintaining quite a bit of air cooling infrastructure. Naturally, a rear door heat exchanger is also, in a way, it's an air cooled approach, but it's close coupled. So to your earlier point, the paths of air travel are much shorter, and really there's a big economic benefit to using rear door heat exchangers when you're dealing with somewhere in the range of about 10 to 14 kilowatts of total load. So that the issue becomes really around compaction, right? Because to your point, it's a pretty expensive solution unless you take my point that we're able to deal with, say, 10 to 14 kilowatts of heat load. Now, at 10 kilowatts of heat load, and let's say we divide that by, say 0.3, right? And say that 70% of the heat is being dealt with by a cold plate or a direct-to-chip technology. That means that, to make the economics work, you need a rack that's at about 30 kilowatts of total load. So in my view, and based on my pretty extensive experience with this application and this approach, I'd say that you really have to go to a hybrid approach with compacted racks to have it make sense.
I can agree, and of course, if we go to chip cooling, you need a connection per rack to the facility side, to the chilled water side. So the connection is made, so the water is in the rack, and you can say, let's also cool the resistance heat that's left from other components, but by a coil in the back door. And if it's only for the last 20 or 30%, it can be a cheaper, smaller, easier coil than, for instance, for 50 kilowatts, of course. So it makes sense, but it's something else than it is applied to today. So if we say, okay, let's look at the optimum, and we say, let's get the heat from the processors and stuff like that, the memory and the other chips that produce a lot of energy, let's capture that in liquid. Yeah, it makes sense because there's a limit to what you can get from an air-cooled body. So it makes sense, but it's a new scope. So if that's the road we want to research. Let's focus on that. Let's describe, and it doesn't have to be in concrete, but let's assume a few figures and let's calculate on that.
Yeah, I agree with you. I think that traditional air cooling is going to make sense, to your point, economically, unless we're getting to compaction of around 30 to 45 kilowatts per rack. And then I think you'll find when you crunch the numbers that it's going to be more economical to deal with the excess heat using a rear door versus a traditional air handling unit.
Yeah, so that's a good example to talk about, and something pretty relative for us. So with the TAC Frontera deal with in Texas, that solution is going to include a hybrid. So it's going to include direct liquid cooling for the chips and a rear door, an active rear door, so that chilled water is supplied to the row-based CDUs. And then the row-based CDU is controlling, obviously, the temperature to a bank of racks. That chilled water is going into the rear door first, so it's neutralizing the heat load in the kind of outgoing air from the servers. And then what you would normally regard as wastewater, that then is going to the chip. So it would be warm water by the time it's actually touching the processors, but that's still sufficient to cool. And then really from there, then it would be hot water, and then it would be going back to the data center. So in that case, from what they were looking to accomplish, they wanted really 100% heat capture. They wanted high TDP processors working within their supercomputer, but also having really a zero footprint in their existing data center. So that's why they wanted a rear door to neutralize the heat temperature. For them, it was really kind of 2-point conversation. One, they were having a very high heat load running their supercomputer, and two, they didn't want to add a large burden onto their existing infrastructure for air handling units, but they already had a large amount of chilled water they could utilize. So it was kind of a win-win in most regards.
All right. Thank you, Joe. Thank you for sharing. Maybe we can talk about maybe we can maybe John and us can share some of the example or some use cases. Very simple use cases about hybrid rack. Then if Joe, if you have any test cases that you can share, Jason, if you can share some test cases about about the hybrid liquid cooling, maybe in the next meeting, I think that'll be great as well.
Yep, sounds good.
Awesome. But I guess one of the downside for the hybrids compared to active or passive rear heat exchanger is, I think someone mentioned about the cost, right? I think one of you mentioned about the cost, right?
Yeah, it's now its solution as it's on the market now. It's not a hybrid. It's a total backdoor cooling, rear door cooling, and the benefits are low energy use, and the cons are in front. The investment is much higher than room cooling, but that's only because the numbers that don't make sense now. If a solution like this, especially the hybrid solution, would be mismarket, the price will come down for sure.
Okay. And then we,
that point you just made. Can you ask him to repeat the point you just made?
so Rana, can you repeat what you just said? I mean, for the points that you made.
Oh, sorry. What's on the market now is a solution that is on the market to make cooling possible for high density, high temperatures, and low energy use. So you can run systems chiller free, but from capex point of view, from investment, it's more expensive than a traditional system. So the benefits are from energy use, but the investment is much higher. But that's due to numbers. It's still sold only a fraction of traditional systems. So when it makes sense and that when it comes common market, the price will drop dramatically, of course.
Yeah, I mean, I agree that once we get to the point that that this become a good solution to cover some HPC market, yeah, I mean there will be some cost drop of this solution.
Yeah, but I guess it would also be interesting to kind of have a frame of reference, right? I mean, at what volume will the price look favorable, right? And maybe if we can have some indication, then that's also very useful for the community, right?
That's rather difficult because that's strongly depending on the ambient. Can you run a system without chillers or not? And what's your energy cost? Because that varies from country to country. So in one country it can make sense. In other country you say I'm never going to do that because the energy is too cheap. So it's always something that has to balance between ambient and energy price.
Yeah, I mean, I agree. I mean, sometime, I mean, at some point, we might also have to look it into, what components are the most, highest component, and then see where we can also optimize those components to reduce the cost for the benefit of the community. But
Yeah, can we make a can we is there anything such as a cost-effective radiator, right?
I mean, we can talk about that maybe in the next meeting or following meetings. I don't want to be too much focusing on the cost and cost optimization at this point. I think we just wanted to know focusing on the concept and defining the definition around that. And then
Totally.
and once we have some prototype and example, then maybe we can looking into which area we should be more optimized and so on. My kind of the next topic is to have a discussion around how should we defining the pressure drop of the real heat exchanger. So defining about we already kind of define delta T requirements and maybe the um, some power level 25 kilowatts, 50 kilowatts, or maybe 33 kilowatts. Um, and based on the CFM per watt, we know that what the CFM should be looks like, or what should be targeted for. Um, but at the same time, is there any other parameter that we should consider to defining the pressure drop in the real heat exchanger? One thought I was thinking is that how much we want to target it for cooling power out of the whole power, either solar power. It depends on the passive or active of the real heat exchanger. Any other thoughts you guys have? So then maybe kind of rephrasing the question, or maybe to the community is, what is the currently typical pressure drop that the real door heat exchanger is targeted for? Maybe 50 kilowatts rack for I don't know, maybe 5,000 PSM.
I think there must be a rule of thumb, right? Like if you want to use a passive renewable heat exchanger, then something like 35 pascals or something like that. I don't know. Ron, uh, you probably have some.
Yeah, it's in our specs, but it's not something I can call up so from head. So I have to look it up because it's depending on the load and amount. It's only depending on the amount of air you're moving through the system, of course.
Yeah.
So it's not something that's a hard figure, but there's of course a figure if you do that amount of air, it will give you a resistance of X, of course. I can put that in an email what the normal commercial coil will do. That's no problem. But again, is it relevant if we're looking at our conversation 10 minutes ago? where we walk on a road where it should be a hybrid solution, it makes sense. The amount of air through the coil will dramatically be less if it's only for 20 or 30%. And if the air is so down significantly, the pressure drop will also go down a lot.
So on
Yeah, go ahead.
So on the topic, Ronald, I guess the amount of air is also a function of the limitation of the heat exchanger performance. And I mean, what I've been reading a lot is that there is a minimum approach velocity or a linear feet per minute requirement to sustain adequate performance of a heat exchanger. Some people say
Uh,
200 RPM, some people say some other number. Is that something that we need to define?
No,
Uh,
agreed. A radar system is basically what we call a low velocity cooler. So you try to get the approach as low as possible, but there's always a balance because the back door is only a certain amount of square feet and it's not bigger than that. So in the end of the day, the amount of air running through it will determine what the approach will be. And to be honest, if we're looking at high temperatures within the hot area of the rack and the chilled water, it isn't so significantly a problem if the approach is 4 degrees or 6 degrees or 8 degrees. It really doesn't matter that much.
right. But I think the question in this case is the approach velocity, not the approach temperature, right? Is there a certain minimum that
No,
needs to be
there's no minimum. But there's a maximum, and when the maximum is there, the approach from water to air will increase. That's the only thing that's happening. There's no minimum.
But is there any minimum for passive conditions? Which mean that is there some trade-off that the sun fan is going to be higher because of some of the back pressure or maybe the pressure drop that the rear-door heat exchanger that
Yeah,
that's
but
the
if there's energy transformation, there is airflow. Otherwise, you couldn't do it. So there is something of airflow there. And for a cooling coil, the slower the air is, the better your approach will be. So from a cooling point of view, the less flow, the better. But that's a delta T thing again.
Mhm.
So it's hanging all together. What is your supply air? What's the delta T over the IT equipment? And which power is needed, and that will determine what the heat dissipation will be and what the delta T will be over the coil.
Yeah, I mean it's kind of a balancing act, right? Because if you lower the airflow, then your delta T goes down. But
Yeah,
if you lower the airflow, your capacity also goes down. So you have to balance that.
agree. Only the thing you always have to remember, the resistance of a coil will be in square root to the pressure drop. So the slower the air, your pressure drop will significantly be better.
Mm, mm. Um, how about, I mean, just curiosity, would that be any um like if we look at um the pressure drop of the server and the pressure drop of the heat exchanger, um, how did the pressure drop of this
I know what you're going to say, but if you look at the server, the room in the server for airflow is so minimum comparing to the coil that the pressure drop within the server will be maybe 90% compared to 10% in the coil because the room for airflow in the server is almost non-existent.
well, is there any kind of the ratio that, if if we have, you know, the pressure drop the rear door heat exchanger is about 5 times greater than, I don't know, maybe I'm just making up a number, maybe 5 times greater than the pressure drop of the system, then the server fans, maybe it's better to go with the active fan.
It will be much lower than that. If you look at the server, and the room for airflow through the server is minimum. If you look at the room for airflow to a backdoor coil, it's large. So the pressure drop for that the IT fan has to cope with for the server itself would be significant more than the cooling door. Because if you look at the square feet where air can flow, it's the whole door. If you look at the server, the air has to go through all the systems, around all the corners, around everything. There's almost no room for air in the server.
But as well, it depends on the sealing of cold to hot of the, let's say, the OCP rack. It has to be very tight. Otherwise, the airflow is not thrown over the heat exchanger.
Sorry, can you repeat that?
So typically, when the server equipment suck on the cold air from the front and blow out the hot air to the rear, there has to be a tight sealing between cold and hot air. So if the sealing is not proper, could be that the hot air removes to the front and is not pushed over the heat exchanger.
Create the sealing within the rack. So the sealing, the separation of intake air and outlet air within a rack is crucial, because there will be a pressure point on the hot side and there will be a low pressure point on the intake.
Of course, and if the pressure drop of the coil is higher than the pressure drop of the, let's say, sealing, then we will not have a success.
True. But again, if we comparison the difficulty that air has traveling through IT equipment in the small spaces compared to the air traveling to a coil of a backdoor.
Absolutely agree.
Okay,
I think maybe we can establish some guidance saying something like, you know, if the IT fans struggle to, you know, reach a situation where they struggle to push air through the door heat exchanger, then in that case an active door is recommended or something like that. Maybe a crossover point, because I think if the door heat exchanger has active fans that make it pressure neutral, that would solve all these issues and IT fan capacity issues and so on and so forth.
It will, of course. Even if you apply bigger fans, there would be more economically than the small fans within a server, always. But the problem is you need an active solution, so you need power again, and you will has to determine the amount of air that the fans will take. And if you're not in control what the ICT equipment needs at that moment, you could also say, okay, let's just get out a certain amount of air and let the fans and the IT equipment do the rest. It's possible, of course.
Sure. I mean, I think
the target of OCP is to harmonize the whole infrastructure. Let's say to harmonize the rack, to harmonize the cooling, and also to harmonize the IT equipment. And at the end of the day, we know the IT equipment, and also because of that, the airflow and the pressure loss of the IT equipment, and also we know the let's say the strengthness of the fan, how many pressure drop they could overcome inside the rear door.
Yeah, I mean, I think this is going to be a topic for over the time, that, you know, what are the parameters we should be considering in the rear door heat exchanger definitions or respect. If you have any thoughts, maybe we can take this offline and maybe through the email and have more discussion in the following meetings. So since we have about 10 minutes, let's talk about what are the topics we would like to cover for the next meeting. I think one of them, catcher, is the some test cases about the hybrid solutions. Maybe John can share some, quick high-level example. Maybe Jason can give us some, test cases that they use on the customer base. Is there any other topic you guys want to cover?
That's it for me.
Okay. Do you want? How about we continue to talk about the heat exchanger spec and what are the critical items that we should be defining in the document? Would that be a good topic? Yeah.
Maybe we can start with the bare version of the document.
The version of the document.
Yeah.
We can
Review a bare version of the document and then start adding meaning.
sure. I mean, we can bring. I can bring it up the the template of the document and then maybe start writing the spec and go over with the community. Anything else you guys want to add on the next topics? I guess that's good for today. By the way, I just wanted to say sorry for all the spam emails happening in a few days. There was some mailing system issue that holding all my emails in their back of their system, and then they push it out when the system get fixed. So I'm sure that you guys get more than one email from me with the same subject. So sorry about that.
Jacob, if you get a chance, can you confirm if my email is on that list?
Sure. Are you also signed up for the emailing subscription for this worksheet?
I thought I had, but I just wanted to maybe confirm.
Okay, now I'll double confirm.
Perfect. Thank you.
Awesome. Yeah, thanks for all the call today. I'll try to post our notes for our meeting minutes for today's meeting. Sometime today or by tomorrow morning. And then we can talk about some of the topic. If you guys have any suggestions about the next topic, send me an email or add them to the note. All right. Thank you, everyone.
Thank you.
Okay, thank you.
Nice day.
Bye.
Bye.